In these slides, we are going to describe and analyze another type of thyristor, that is the gate turn-off thyristor, very often abbreviated like GTO. What we've seen before is that the SCR, the classical thyristor, can only be used in AC circuits with the input voltage that reverses, and this device is able to switch on and off, and in this case the device is switched off by the voltage. When you have a DC circuit like the DC-DC converter, buck boost, a device like this, you cannot use an SCR because you don't have the reverse voltage able to switch off the device. In this case, for low power, bipolar junction transistors were used. Lately, when the power MOS became available at low cost, this has been very often the preferred choice. However, for high power and circuits working with DC voltage, input voltage, there is no other way than using a different device, and this is the device. The resulting device has been the GTO, that is used for DC circuits, and it is still a device with a very high power capability, high current capability. From the structure point of view, the GTO is basically an SCR that is possible to be switched off when the anode voltage is positive. This is done by applying a negative gate current pulse to the device. The switch on is actually obtained with a positive gate current pulse, similarly to the SCR. The electrical symbol for the GTO is the one in this figure, and as you can see, there is this double arrow here that indicates the bidirectional gate current that is able to switch the device on and off. From the physics point of view, the GTO is still based on a 4-layer NPN-PN structure. The on-state characteristics and the turn-on behavior is similar to the one of the SCR, taking into account that there can be difference on the latching current or holding current in terms of absolute values. Another important aspect is that the GTO does not require to withstand very high reverse voltages. This is common for an SCR that needs to support more or less the same forward voltage and the same reverse voltage working with AC voltage. This is not the case for a GTO that can work with the positive, always in the same direction, DC voltage. In this case, it is possible to, while for the SCR, asymmetrical structure are not possible, more or less, because the reverse blocking capability is very small, for the GTOs, the asymmetrical structure are possible. In the following slides, we will focus on the turn-off capability and how to turn off the device. That is the real difference between the GTO and the SCR. We can approximately study the turn-off of the GTO using the circuital model with two BJTs that we have seen before. It is then clear that there are very big approximations in this model, because if this model was correct also for the SCR, it would be possible to switch off also the classical thyristor. But we know this is not possible. This means that in this model there are big approximation. But this, in any case, allows us to understand some of the aspects of the GTO. First of all, if we analyze this 2 BJTs model, we know that these in the on state, these two devices are actually in a hard saturation, and you don't need gate current because this BJT is on and provides a large collector current. This large collector current is actually the base current for this BJT that in the same way amplifies this current and provides a very big base current to this device. They will work together, bringing one and the other in the hard saturation, and the device is on. But if we extract a very large gate current, imagine that this gate current is actually equal to IC1 or even equal to the anode current. There is no current left for the base driving of this Q2 transistor. This Q2 transistor will switch off. There will be no base current for the PNP transistor near the anode terminal, and the device will switch off. In this model, it is possible to switch off the thyristor with a negative gate pulse on the gate, negative pulse on the gate. However, the condition that I explained with a very large current on the gate is too strong. It is actually possible to demonstrate that the latching state, the on state, is maintained by the regenerative feedback action, and it is enough to force the Q2 transistor out of the saturation to stop this regenerative action. When this device exits from the hard saturation, this base to collector junction is reverse biased, and this means that also the other device will go in the active region, and in the end both of them will switch off. Now we can write that the Q2 transistor is in saturation if the base current is larger than the base current that we need to stay in the active region. The active region, in the active region, the collector current is beta 2 multiplied IB 2, and hence if the base current is larger than IC2 divided beta 2, the device is in saturation. This means that our no saturation equation is base current smaller than collector current divided beta. Now beta, we know, is the ratio between alpha 2 divided 1 minus alpha 2. Recalling again the schematics of the two transistors, here we have also the gate current. We know that this IC1 is alpha 1 multiplied anode current. We know that this IC2 is alpha 2 multiplied by the cathode current. And we also know that the sum of these two currents is the anode current. This means that this current is also equal to 1 minus alpha 1 multiplied anode current. For the base current of the Q2 transistor that we want to have smaller than this value, we can write that it is IC1 minus the gate current. also equal to alpha 1 multiplied anode current minus Ig current. Instead of using the anode current, we can also use this equation that tells us that IC2 is equal to 1 minus alpha 1 multiplied IA. We can substitute this equation in 6 and we obtain that the gate current must be larger, the base current must be smaller, but since the base there is a minus, we have the gate current must be larger than alpha 1 multiplied by the anode current minus 1 minus alpha 1 divided beta 2 anode current. We can substitute beta 2 with this equation here to get this relation. This can be simplified to get that the gate current is enough that is larger than the anode current multiplied by alpha 1 plus alpha 2 minus 1 divided alpha 2. It is better to write this relation like Ig first must be larger than the anode current divided by beta off, that is the turn-off current gain. That is the ratio between the anode current and the gate current that we need to switch the device off. We want a very large turn-off gain. If the gain is very large, for example, if the gain is 10, it means that the gate current is 1/10 of the anode current. If the beta of the turn-off gain would be 100, it means that we need a current that is 100 times smaller than the anode current in order to switch off the device. The reality is much worse. The actual values for the gain go from 1 to 5, maximum 10. This means that you'll need for a 100 amps application, the pulse of the gain must be between 20 and 50 amps of extracted current in order to switch off the device. A current that is in the order of magnitude of the main current. This actually is the best that you can do because you don't have any other device, but with such a small beta you are losing the main point of having a switch. A switch is something that uses very small energy to control a large amount of energy. You want a small activation to control a large flow, in this case of current. In this case, the activation is more or less in the same order of magnitude of the current that you control. But this is the best that we have, and we have to work with it. It is clear that in order to have a high turn-off gain, we need a large gain of the alpha 2 transistor, the NPN transistor, and a denominator alpha 1 plus alpha 2 minus 1 that is larger, that must be small, and should approach 0. That is, means that the sum of the gains of in the latching state. In latching state, the gain, the turnover point is alpha 1 plus alpha 2 is equal to 1. In the hard saturation, the sum of the alphas is larger than 1. And we want to have them very close to 1 in order to have a large gain. But this means that it is difficult. We are almost switching off the device. If we are close to the turnover point, Finally, this means that we are increasing the holding and triggering current. Becomes difficult to trigger the device, and when the device is on, is always there that he wants to switch off. We are at the edge of the latching state. And this means also that we are increasing the forward voltage drop of the GTO with respect to the classical thyristor, and this is expected. You are asking for an added feature, that is the switch off capability. You are paying this with something higher power or on-state power voltage drop, for example. There is obviously a trade-off between on-state voltage drop and turn-off gain. Typical GTO devices will have a turn-off gain in the range of 5 to 10, and as a consequence, in order to switch a 1000 amp GTO device, you will need 200 amps, 100 amps of current in the base driving circuit. This means that the main circuit is a huge power electronic circuit, the driving circuit is a medium power circuit, and that probably needs another low power circuit to be controlled. You cannot control with very low power. The analysis that we've shown, if we apply this analysis to a BJT, to an SCR, we see that it is possible to turn off the GTO, but with the conventional value, the beta, the off beta, the turn off gain is about 1. This is not acceptable. You don't want to switch the device off carrying the entire anode current. In order to improve this value, another important aspect is that we are also completely neglecting the transverse effect, because we said before that the SCR, the classical thyristor, cannot be switched off through the gate because we have the transverse effect here that will keep the device on when we try to extract a large current. And this is completely neglected in our previous analysis. Finally, this means that we need to slightly change the structure of the GTO in order, first of all, to be closer to what we expected, the large alpha 2 value, and the sum of alpha 1 plus alpha 2 very close to unity in the on state. We also need to reduce the base spreading resistance, because when we extract the current, we don't want to switch off the NPN transistor, and this means that the current flowing here from here to here doesn't have to switch on this junction. Finally, this is the structure that is usually implemented in a GTO. This is one example. There are many variants, obviously. There is a not planar structure technology. In this case, there is an etching. The cathode contacts are raised above the base contacts, the gate contacts. The gate contacts, you can see here, they are quite big. The area is in the order, more or less the same area of the cathode. And this also reduces the base spreading resistance because there is a lot of contact. This means that we need a very finely interdigitated structure for the gate. The GTO is then realized more or less like this. Here we also see these shorts, this short circuit to the anode contact. We have seen before the cathode shorts. The cathode shorts, we said they were shorts here. They will reduce the alpha 2. They reduce the gain of this NPN transistor, and they will improve the voltage the voltage derivative capability of the thyristor unit turn off. But this is forbidden for a GTO, because in a GTO we want to have large alpha 2 value. Then no cathode shorts, maybe anode shorts from this other side to reduce the gain of alpha 1, but not reducing the gain of alpha 2. This is the explanation of what we have said before. We have this gate cathode contact obtained by etching. The cathode and the gate has a high periphery area ratio, and the charge removal from the cathode is more effective. Doping and thickness of the gate layer are chosen to obtain a quite high value of alpha 2 in order to get a turn-off beta of around 5. The anode region is made of alternate P plus and N plus region. These are anode shorts. In this way, they allow a faster removal of the stored charge, in the sense that also in this case, this N plus will reduce the efficiency of this P plus holes injection region, and in the end you will have less charge stored here, and this will prevent, for example, the unwanted turn on during the voltage increase of the voltage anode to cathode voltage. This is another view, a three-dimensional view of the GTO, just to show what it can look like for a real device. As you can see, these cathodes are spread along chip surface area. There is gate contact that is it has a very large area. And also we have the raised contacts for the cathode. In this case, we have the anode shorts. It is also possible to have a symmetrical structure, as we said before. In this case, we will have a buffer layer here before the P plus region without the anode shorts, probably. The drift region will be shorter in this case, and will reduce the amount of stored charge. The buffer layer that we implement here can also be used to decrease the base to emitter junction efficiency and reduces its gain. This can be better explained here. When you have the symmetrical structure, if you have the anode here, this is P plus, then you have the drift region, then you have the base, the drift region is N minus, then you have the base, and then you have the cathode contact. This PNP transistor here, the emitter is here, this base junction, and the efficiency of the emitter efficiency is very good, because this is very highly doped and this is very lowly doped. This means that minority kernels injection in the emitter is small with respect to the holes injection from the emitter, and this is good for the emitter efficiency. Ideally, we want only holes injected from here. Okay, the base transport factor is quite small on the other hand, because this is very long. But if we want to reduce the efficiency of this region, the only way is reducing the doping here. But this cannot be done, because if this doping is too low, this is no more a ohmic contact. This is a shock contact and doesn't work in our application. But if you have this is symmetrical. If you have an asymmetrical structure, the things change, because the asymmetrical structure will be shorter. Let's say to here, you will have the anode contact here, then the cathode contact is more or less the same. This is N plus, this is P. Then you have the drift region that is N minus, and here you have the buffer layer that is P. This is P plus and this is P. Now the homing contact is guaranteed by this P plus diffusion, and you can play on the doping of this region to change the emitter efficiency because now the emitter is here, and you can reduce the doping of the buffer layer to reduce the efficiency if you want. This buffer layer is the one in charge of stopping the electric field that will go like this in the blocking state. The GTO, the explanation of the GTO is not very rough in this lecture. It must be said, the GTO is very complicated. We don't go in all the details. The basic operations are not easy to understand. We'll show here the basic operations of the device, focusing on an asymmetrical structure. We are just repeating some of the concepts that have been explained before, but this is to gain a better insight in the physics of the device. Let's now focus on this GTO device, this schematically shown here. N plus cathode, base P diffusion, N minus drift region, buffer layer N plus. Then we have the P plus anode contact. The PNP transistor, the emitter efficiency depends on this N plus, P plus to N plus doping. This was N, sorry, obviously this was N. Now the emitter efficiency is this between this P plus and this N plus region, and working on this doping we can modify the gain. Here the raised contact is not shown in this scheme. Turning on the device. This is very similar to the SCR. There is an injection of current from the gate. The cathode is at ground voltage and the anode is at higher voltage. This current is made of holes. These holes here are the base current for this NPN transistor. As a consequence, there are these NPN transistors which is on, and the emitter injects electrons into the base. They will flow through the base without losing too many carriers because the base is thin, more or less. And they go into the N- base drift region. Here they behave like base current for this transistor, for this PNP transistor. And this means that there is an injection of holes from the P plus junction into this base and into the collector. These holes arrive here and they work like base current for this NPN transistor. Here in this schematic view you can see one hole here that causes 3 holes coming from here, means that there is a gain. When the latching state is established, alpha 1 plus alpha 2 higher than 1, there is no need of gate current to keep the current flowing. In the on state, what happens in the on state? In the on state, there is a high level of plasma that is present throughout the device. Here it is shown only here, only in this region, but it is everywhere in the device. If I plot the carrier concentration in the device, you can see that as a function of the current density, there is this very high injection. We can reach very high current density, 1000 amps per centimeter square. It's a very large current for a device, silicon device. This is also shown. There are electrons injected from the N+ cathode and holes injected from the P+ anode. The various carriers here have a different life, showing that there are carriers that are injected from the P+ region. These are holes that recombine here, and they are the base current for this NPN transistor. For every hole that recombines here, there is one electron ejected from here. In the same way, there are electrons that work as base current for this PNP transistor, and they recombine here, and with one hole that is injected from the anode. But there are also carriers that do not recombine because the transport factor is good, and there are holes that direct arrive as current to the gate, and vice versa. And they recombine here directly with other with the electron. The holes recombine with the electrons here, and the electrons recombine with the holes here. In this region of the device is more or less similar to a PIN diode in full conduction. The high injection regime means that this N+ region is connected to this P+ region. The base region is just over K, flooded with carriers. And if you are in the high injection regime here, you can neglect more or less that there is a P diffusion below. Turning off the device. There is an whole current that is extracted from the gate, from the P+ gate. This is able to cut the feedback, the positive feedback of the thyristor. As you can see, firstly, the current through the PNP transistor will be lowered because the base current or the PNP transistor that is made of electrons is reduced. This means that we will reduce the base current for the NPN transistor, and in the end this is not enough to keep the saturation, and we will reach the complete turn-off. During the turn-off, however, the plasma is squeezed into the center of the cathode, because we are extracting plasma from here and from here, and from here. And this means that here we have depletion regions that start to develop, while in the middle of the cathode there is still plasma. In this case, we need to be careful. Filamentation means that if the current is more or less the same, these regions can heat up, and with the well-known thermal instability problems of the GTO. In order to prevent this effect, we need to have a very high density of gates and cathode contacts in order to prevent the presence of wide filaments that will stay there for a long time. As you can see here, you see some holes that instead of recombining in this base layer and acting as a base current for the NPN transistor, they are diverted in the P+ contacts of the gate, while other carriers still keep flowing from the cathode to the anode and are part of the direct current of the GTO. The anode shorts that were not shown in the previous plot, but that were shown here, for example, they will help in removing the storage charge accumulated near the anode junction that would be otherwise blocked by the NP junction. This will improve the switching speed and the reverse recovery. The dynamics of these devices is also dependent, like for the PIN diodes, from the lifetime in the low doped region. If you use some kind of lifetime control techniques to reduce the lifetime into the drift region, this will obviously reduce the switch off time, the reverse recovery time, but the on-state voltage drop will be larger. There is also in this case a trade-off between reverse recovery and forward losses, and the optimal choice will depend on the application, which is the intended switching frequency, which is the expected on-state voltage drop. Anode shorts will provide you a significant limitation on the ratings, because they will prevent you the reverting of the voltage and the reverse breakdown voltage. This concludes our GTO analysis.